Mean that if f of x is a linear term, then. So you have f of x and k of x and it's degree
That's
one.
why ax plus b. That's
Right.
what yeah.
So does that mean that the root of that is always contained in k?
Yes.
As soon as you factor it into linears, you're contained within whatever field you're working.
That's right. I mean, and if you take an f of x that's irreducible and you can factor it into linears, then it's already in degree one,
Right.
right? Because otherwise it wouldn't be irreducible.
Wait, if you have a minimal polynomial f and you can factor it into irreducibles?
Now, if it's irreducible and I can factor it into linears, then it's linear.
Oh, because it's already in.
That's right.
Oh, okay.
Right.
I was like, wait. So if you have like x plus one.
Dr. Covino, how you had some way of figuring out what the polynomial was given roots? Like, for example, in the rationals, like what was the process there? Because I completely forgot. You know, like if you're given
Oh,
like,
that specific example?
or no,
I
like
just worked it for that specific
Okay.
example. I mean, if you give me,
I don't find a real adult.
alpha is.
I had to look it up. I had to look up. And it was like the most, and they're just like. It's like.
oh no, I meant finding like given the root. Like given a number, find the polynomial, it is
Well,
a root.
where I'm going.
Oh, sure.
Both of these are Eisenstein irreducible polynomials. They also have derivatives that are non. Oh. There we go. Now they have derivatives that are non-negative, which means that they can have at most one real root. So just to be specific, if here's the minimal polynomial for alpha, here's the minimal polynomial for beta, minimal polynomial for alpha plus beta, I can figure it out, but you're gonna waste your review session, right? Because it'll take a while for me to do it.
Sure.
Right. And the process is, you know, I know what all the conjugates of these, right? Because I know that this thing has 5 roots and alpha, which is alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and they satisfy these relations to make this polynomial work and here, and I can mess around with it and massage it until I get something. The polynomial will be, well, actually, the only choices here are, if I can tell you. So if you start with Q here. This is an extension of degree 3. This is degree 5. And to have this thing in here, right?
It's gonna be 15.
Well, so notice this extension here is degree 5, so there's no way that beta lives in here, right? Because that would create a subfield in here and that's impossible, right? Yeah, it's going to be 15. And in fact, those are the only alternatives really, because I know this extension here is 15. And the reason I know this is because 5 and 3 are relatively prime. So for sure that's got to happen. So this is degree 15. So that means that when I look at Q alpha beta, or alpha plus beta, then there's only 4 possibilities. Number 1, alpha plus beta is already in Q. And that's impossible, right? Because this one doesn't contain something, it doesn't contain a subfield of degree 3, for example. So it's got to be one of these, but it can't, well, it certainly can't be Q beta. This can't be Q beta because if alpha plus beta is in here, then alpha's in here and you've got the same problem you did before, and it can't be that. Now, theoretically, you might consider the possibility that there is another fifth degree intermediate extension. But you can discount that as well. This one's gonna be all the way up top here. So whatever the minimum polynomial for alpha plus beta.
And is there not relatively prime? Is it just the least common?
Not necessarily. So, let me give you, a couple of examples. This is like extreme sort of in its stupidity, I think. This is a big fat cheat, right? Because this is actually the same thing as this. And so this is all just a big extension of degree two. On the other hand, if you do this, this is actually genuinely degree four, even though these both are extensions of degree two, right? Basically, one way to see this is you can prove that when you make this jump here, radical three is not in there. In fact, let me prove that just for giggles. Oh. So when I make the jump here, I claim. Oh, wait a minute. No, I think Clemson should just give me this classroom, don't you?
It'd be great.
It's
so
very-
convenient.
That's right.
Perfectly sized.
I could sort of like being a real bad neighbor or something during other people's classes, so they never want to come here again. That's probably not gonna work out well for them, though. Claim. Radical three is not in. Well, let's prove this. The first thing I'm gonna observe is these two are the same, of course, because radical two is algebraic, right? And so this makes me justifying this claim easier. Let's assume radical three is equal to a plus b radical two, some a, b in the rational numbers. Right? Well, let's just square both sides. Agree. Now, these players here, three a squared and two b squared, they're all rational numbers. And the set one radical two is a linearly independent set over Q, right? And so really, you can think of this as zero is this big fat rational number, this thing minus three, plus two AB times this, times radical two. And because of the fact that that's a basis, this implies two AB of zero, right? Since we're talking about rational cases, we've now got two cases. If A equals zero, then what this gives me is three equals two b squared, and that's a contradiction. I can take this out further if you want, but is that clear to you all that two is, you could write this as a fraction. Let me go through the details of this just for giggles, suppose B equals, X over Y, X, Y in the integers. And of course, Y is not 0. Then this gives me the equation 3y squared. We can also assume here in the GCD, xy equals 1. That is, I can assume that my fraction is reduced, save myself a little trouble. Look at this equation here in the integers. Now it's easier to deal with. This implies 3 divides x squared, which implies 3 divides x. Because 3 doesn't divide 2, and 3 and 2 are relatively prime, so 3 has to divide x squared. But 3 is prime, so it has to divide x, right? So x is equal to 3k. And this equation here gives 3y squared equals 2, well, times 9. So I guess that would be 18k squared, right? Therefore, y squared is 6k squared, which implies 3 divides y squared, which implies 3 divides y. And there's your contradiction. Because 3 divides both x and y, which is contradicts that I can pick the fraction to the numerator denominator. Okay with it? So there's a more complete proof. But at any rate, there is no square of a rational times 2 that's 3. No more from that. Case 2, b equals 0. In this case, I get, and a very similar proof shows that there's no rational that squares to 3. In fact, you probably saw something like that in 3190 would be my guess. So, where are we at? Radical 3 is not in Q radical 2. Now notice radical 3 is the root of a quadratic polynomial over Q. So in particular, it's the root of some polynomial over Q radical 2. I know it's the root of a quadratic polynomial over this. And since it's not in there, there's no way it can be the root of a linear polynomial. So you have an honest to goodness jump of 2 here as well.
Why do we have 2a equals 0?
Right. Think of it this way. 0 plus 0 radical 2 is equal to a squared b squared minus 3 plus 2ab radical 2. These are basis elements, just equate them, right? The two, in fact, I could just put a 0 here. The set 1 and radical 2 is linearly independent set. So in fact, both of these, not only does 2ab have to be 0, but this has to be 0 as well. Okay with that? Yes.
If we have two field extensions of a base field, let's just take Q, and one is like a degree 4 extension. So we say the degree of the extension, like that is the terminology, not like rank.
The degree.
Degree. So the degree of the extension is 4 for one and 2 for the other, and you're trying to find a field that contains both. In general, can we say anything? It's, I mean, less than or equal to 8.
Well, so here's what we know actually, I think from the last homework maybe. So you're talking about this situation here.
Yes.
So in this particular situation, I can do this. So here's what it is. And it's gotta be at least four, right? Cause you're assuming that thing's four, right? So there's no way it's gonna be less than four. So this has gotta be 4 or 8.
So,
It would be 4 if the degree 4 extension contains the degree 2 extension. And if it doesn't, then it's gonna be a degree 8.
and then what is F1, F2 exactly? Like,
This is the composite. This is the smallest field that contains all of F1 and all of F2. So think of it as generated by the union of these two. And of course, you made it easier on me because of the fact that these are both finite extensions. I know in this case, the composite is actually algebraic.
For that part, I know how you got like the a squared plus 2b squared minus 3 plus that equals 0. But where does the 0 plus 0 square root 2 come from?
Because what's left on the other side is 0. So I wrote that off.
Oh, so you can.
I wrote it out in chromatic form and said, okay, just compare the basis elements. This must be equal to this, and this must be equal to this.
Mm.
Yeah, because basis
Oh.
representations are unique. Or you could just take this straight up from the linear independence and say, well, look, this thing adds up to 0. And 1 and radical 2 are linearly independent sets. That means that both these coefficients, namely this and the 2AB part, they have to both be 0. Because the set's linearly independent. Yes.
should we expect anything about, flatness or like anything from module theory or no?
Did I even tell you what flatness is?
It
Oh,
was
you barely
12.9. It like skipped, but it's in the notes. It's in the.
Oh, it's if I didn't talk about it.
But, anything from module theory or no?
I don't even remember. I mean, so, I sort of thought of this as sort of starting about with the
The
modules over a PID kind of thing, right? Do you know how to do all that kind of crap with the invariant factors and the whatnots?
I wouldn't mind an example personally.
We do have an example.
Okay.
Exam, if you wanna do that.
Yes, let's do that.
It's a baby problem.
I mean, you could also put your.
Is it a homework or an exam?
It's from the exam. You gave invariant fact wait.
Is this something I should look on my computer or is it?
I have it on mine if you just want to use it as reference, but it'd be easier if you look for it.
Yeah, it's probably easier. So what is it?
It's question 2 from the exam you gave in 2013.
Exam 2, 2013. Oh, okay. So you have a linear transformation from T from V to V, and it has variant factors. Variant factors. How many of them do I have? 1, 2, 3. Okay. 1. X minus A. X minus B. 2. X minus A on the squared. X minus B. And number 3. X minus A squared. X minus B squared. Okay. Where A and B and F are distinct. Yes, they're not. Okay, so. What is it? It's the dimension of the vector space.
No.
Good, it is 9, right? Because this has degree 2, this has degree 3, this has degree 4, and the product of the invariant factors should be the characteristic polynomial. So you've got a 9th degree characteristic polynomial, so it should be a 9 by 9 matrix. Everybody cool with that?
And is that always true that it's just the product of the invariant factor or the degree of
Yes.
the invariant?
Yes, the characteristic polynomial is always the product of the invariant factor or the elementary divisors, if that's what butters your bread. So. How about? What is the minimal poly? I don't know what the minimal polynomial is.
The largest, invariant factor.
Right. By largest, what he means is the one that is divisible by all the other ones in that sense, right? Largest factor. Which in this case is x minus a squared, x minus b squared. So that should be the minimal polynomial. This thing.
Dr. Gordon,
Mm-hmm.
do you always have that the invariant factors like divide one another?
Yes. Yeah, they have to. They sequentially divide.
Okay.
Yeah.
So like there is no ordering.
Yes, that's right. What else we got? Oh, what is the characteristic polynomial? Well, there we go. We now know what this is. C. Beauty. I guess it's x minus a. X minus b. 4. That should be the characteristic polynomial. Find the elementary divisors. So we're working. Okay. So elementary divisors. You know how to pick these out? Well, I think usually when I do this, I'll almost always start with the elementary divisors, work the other way, but it's 6 1, half dozen the other. What are they? Okay, good. So these are the prime powers dividing everything. And I know that x minus a is prime because it's linear, right? I notice I didn't tell you what the field was here, but I get around that because everything here in my particular example breaks down into linear. So there's no question about whether it's prime or not, right? If I had something up there like x squared plus a squared, then you might start cussing at me if I said, can you reduce this or not, right? Because you got to know in the field whether that breaks down any further or not. But here, everything's linear power, so there's no worries. And what do we got here? X minus b. X minus b. X minus b squared. There we go. Everybody groovy on that?
Or part C, if you had like one other factor that's like x minus 1 or something, would you just add that? Like all you did was add the like polynomials together and the.
So your question's a tricky one. Okay, let's say A and B are not 1, okay? So she wants to have another factor of x minus 1, right? There's only one place to put it in the list of invariant factors. Everybody know where?
At the last one.
You gotta tack it to the last one, right? Because this has to divide this has to divide this. So you can't put an x minus 1 here because then. So if there was another x minus 1, ding, 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 it would go there. And it would change this by there'd be an extra x minus 1 here.
Okay.
And it would change this by there'd be an x minus 1 here.
Okay.
Is that clear enough?
Dr. Quayle,
Yeah.
if you, for some reason, put like a +1 for the 3.
+1.
Yeah, so if you had like a sum, would that give you information about the field?
I'm sorry, I don't understand the question. Are you talking about on this one right here?
Yes, on the third level, and then you have like plus some constant with that.
Oh, plus this?
Yeah.
Oh, well, that doesn't help me much because when I have the invariant factors, I want to factor it down. So if you put a plus constant here, I want to multiply this all out, see how to refactor it.
Okay,
And then it's probably not gonna work with these anyway,
sure.
because it's not, these are not gonna divide it anymore. If that
Sure.
constant's not zero, so. So, I got a big 15-pointer right here for the Jordan form, the rational canonical form, primary rational canonical. So that's why it's 15. There's 3 of these. So,
So that's 5 each.
yeah, I guess that's,
Basic math.
it's been a few years ago, as you can see, but I'm sure that's what it was. Let's do the Jordan form first. Now, the Jordan form, and actually, there's something else I'm gonna have to do here. I'm gonna rewrite these elementary divisors this way. And anyway, and I might as well multiply these out. This bad boy is x squared minus a plus b x plus ab. This is whatever I get my, why did I do this to these poor people? This is going to be, well, it's gonna be that times x minus b, so it's gonna be x cubed. Minus b, so it's gonna be minus 2a plus b x squared. A squared to b x, right? Yeah, minus ba squared, I reckon. And then to get this one, I guess I gotta multiply this crap by x minus b, so this is x4. That's gonna be minus b minus 2a, so this is minus 2a plus 2b. I guess that makes sense, it should be symmetric now, shouldn't it? X cubed. That's x cubed. See, that's gonna be, so it's all gonna be big 5 plus, isn't it? It's gonna be a squared, 2ab plus another 2ab. Right, a squared. Yeah, that looks like x minus b here is going to be minus 2a squared b. Do it again.
The first thing.
2ab squared. Yes, again, it should be symmetric. And then it's going to be plus a squared b squared. There we go. All right, so that's just kind of preparation for what I'm going to do. The Jordan canonical form for this matrix. The Jordan canonical form and the primary rational canonical form key off the elementary divisors, right? And in Jordan form, you have to make sure that the elementary divisors factor into powers of linears, right? But it looks to me like for the eigenvalue A, I'm going to have 3 blocks. I'm going to have A, this is a 9 by 9 matrix, so then I'm going to have A1, 0A, A1, 0A. So that takes care of these animals. And then for the B, I'm going to have a single B block. a single B block, and then a 2B block. 1, 2, 3, 4, 5, 6, 7, 8, 9, and the rest is zeros. So that's what the Jordan canonical form is. Is everybody with me on that? Okay, so how about the primary rational canonical form? For this one, I also key on the elementary divisors for the primary one. But now they're multiplied out like this. So I'm gonna go in order again. So again, I just get an A block for the first one. And then I get a block that looks like this, 0, 1. And then I get minus A squared plus 2A. And then I get another block that looks exactly like that, 0, 1, minus A squared, 2A. And now I'll get 2 blocks with a single CB. And then I get a similar kind of 2 block that I get before, 0, 1, minus B squared, 2B. 2, 3, 4, 5, 6, 7, 8, 9. Good. And everything else again is zeros. So that's the primary rational form, right? Right, okay, so far. Rational canonical form. Yeah, the biggest pain in the butt was actually just multiplying it out. And if you're in a hurry, by the way, nobody likes multiplying this out. I would say and just make the block, right? Where we all know that we're smart enough to figure out what A, B, C, D, and E are, right? So just do that, go quickly. If you want to come by, doll up your test after you're done with everything else, that's great. But I would just do this if you can't multiply these out quickly. Rational canonical form. This, of course, keys on the invariant factors. And so I'll just take this bit by bit. 0, 1, negative AB, and then A plus B. There's my first block. Then I'll get a 3 block of this. 0, 1, 0, 0, 0, 1, and A squared B, minus A squared minus 2AB, and 2A plus B. It's hard to read. Like that. And I'm gonna spread this one out more. 0, 1, 0, 0. Do some spreading. 0, 0, 1, 0, 0, 0, 0, 1. And for this last one, I get minus A squared B squared. I get 2A squared B plus 2AB squared. And then I get this mess, minus A squared minus 4AB minus B squared. And finally, I get 2A plus 2B. And there it is. Everybody okay with that?
How many points would we get if we wrote that?
Wrote what? Just
The
the,
A, B. Like if we didn't, if we were just like, this is a 4th degree polynomial. This is gonna be.
probably all of them. Okay, so is that kind of cleared up for y'all? Yes,
So Jordan depends on linear terms. The primary rational canonical form depends on the elementary divisors. Then the,
well, both ones you just named depend on elementary divisors.
okay,
But to be able to do the Jordan form,
Yeah.
you have to be able to factor the elementary divisors down into linears, right? So the problem is if you were trying to do something over, say, rational numbers,
Hmm.
x squared plus one is an irreducible polynomial over rational numbers, right?
sure,
So you can go to town and do a primary rational canonical form of that, or a rational. There you go. You can't do a Jordan form of that
gotcha,
because you can't pull that down into the linears that you need.
right, okay. And all of the variant factors are gonna differ, like, if you take the if you see the difference between two adjacent ones, are they only ever gonna depend on a linear? Like, if I take two and I divide by one, then I get a linear, but that.
Oh, no.
Not sure.
I mean, you could have invariant factors. X squared plus one, x squared plus one to the 10th times x squared,
Mhm.
x squared plus one to the 10th times x cubed times x squared plus x plus one to the cubed. You can just, I mean, anything, any chain that you can make up where this divides this divides this is a possibility for invariant factors.
In the question above, or in like question one, part S. Um. Define what T invariant is. Is that like? Is that like the phi invariant, like it's?
That's
like-
right. That's
okay.
exactly right. What that means is, when you take. Right, so if you take the subspace, so you have T that goes from B to B. So if you have T goes from B to V. In fact, this was very much, this is almost exactly like the stable fields we were talking about. E and V is T invariant. If T of E is contained. Right, so in particular, if E is the kernel of that linear transformation, that'll always be T invariant, right? The entire space V is T invariant, right? Because by definition, the linear transformation goes from P to V. Right. Yes,
So with this, what we're doing is taking T, the transformation, and finding which subspaces are invariant, and then those are represented by each of the factors.
yeah, that's right,
Okay,
that's right.
and so we construct our forms from.
That's how
the
these blocks are
spaces.
working. That's right. That's exactly right.
And then for E, which is above that, how does one construct an extension field containing a root of F? Does the root have to be like, if I did like, if I said alpha is a root of F and I just did F adjoin alpha, even if alpha is in F, is that not an extension field?
Well, so let's see, I think it's in the polynomial, it's irreducible degree bigger than one, is that right? Oh, an irreducible poly of degree at least one. Yeah, so that problem entertains the possibility that the root's already in there. Right, so I could give you the rational numbers, right? And I could give you the polynomial x plus one. give me a field extension of the rationals where x plus one has a root, the rational numbers itself,
Okay,
right? And so here, this is really kind of what I was looking for there. So irreducible. And of course, there are no irreducible polynomials at 3, 0, but just for emphasis. Here's the way you construct a field. That's the construction right there. You just take this polynomial here in fx. Now fx is it's a principal ideal domain. In fact, it's Euclidean domain, right? And that means f of x is irreducible in here. And this is a PID, so it's UFD. So irreducible means prime. So this is a prime polynomial, right? And bonus, this is a PID. So this prime polynomial actually generates a maximal ideal. Not just a prime ideal, but maximal, because fx is a principal ideal domain. That means that this quotient structure is a field, right? Because it's a domain, or well, actually any ring modded up by maximal ideal. Yes.
Is this always finite?
The extension is finite, but it's not a finite field.
Right, but it is finite.
That's right. It's the extension is of degree n, where n is the degree of this polynomial.
Right.
And for example, if the root's already in there, then the polynomial is of degree 1, and it's an extension of degree 1. And so k would be isomorphic to f in this case.
How do you get the infinite degree?
By joining an element, you have to join a transcendental element.
But then you get, but you still have infinite algebraic extensions though? Like algebraic extensions.
Yeah, but to get an infinite algebraic extension, it can't be the root of just one polynomial, can it? Right? Yeah, it has to be a root of a whole. In fact, it can't even be a root of finitely many polynomials, because if you have finitely many polynomials, you multiply them all together, now you got one polynomial.
Right.
So it has to be, you have to adjoin roots for infinitely many polynomials.
and then for part D, give an example, or give an example of a transcendental extension of f. If I just say like, let k be a bigger, or like, let k be a field containing f, and I say alpha is in k that's not algebraic in f, k join alpha.
You're right in spirit, but I might criticize you by saying, but this is all supposing that you can find such a thing, right? So how can you actually, so give an example of a transcendental extension of that? There's a standard go-to. Does anybody know what it is?
Adjoint pi, or q adjoint pi.
Yeah, but I didn't say Q, I said F.
Oh.
Just take a polynomial, just take a variable, an indeterminate over X. Now look at the field. Look at this extension here. Actually, I should do that. Right, because in particular, the rational functions over F contain all polynomials in F, and none of those polynomials are 0, right? So X is not algebraic, right? X is like a variable. So this mathematical structure, this is a field. This is right. This is F, any field you want. This is rational functions in F. This is kind of the go-to for idea for a transcendental extension. And notice you can make these very big, because if you're not satisfied with f of x, you can stick on another variable Y, another variable Z, you can go to town with this, and you can make very big transcendental extensions.
So an indeterminate is just something that's like, you can replace it with, like, some.
Yeah, but don't think of it that way, just think of it as a symbol, it's just an abstract symbol,
Okay,
and it's got no algebraic relations with F.
okay, but
Right.
transcendental is like, it's just not a root. Or
That's
it's
right.
not algebraic.
Right, an element is algebraic if it has a polynomial relation with the coefficients in a certain sense in F. Right, it's transcendental if it doesn't, right? And so when you learn like polynomials, even back in high school, when you start playing around with these polynomials, you can add two polynomials, but you don't expect a polynomial just to be so if you took the polynomial x squared plus x plus one, for example, that is not zero. For you to set that equal to zero and solve it, what you're doing is you're finding a value to plug in for x for which that is zero, right? But the polynomial itself, x squared plus x plus one, is not zero, right? Because it's an indeterminate, right? And it's algebraically unrelated to whatever field you're in, right? Does that make sense?
Dr. Gordon,
Hmm?
when we have like the infinite algebraic extensions, are you are you constantly modding out by more, like infinitely many irreducible polynomials that are not like divisible by each other?
That's kind of sloppy, but in a certain sense, that's kind of how it happens. After we get through the Galois theory, one of the things I might do is what's true is if I give you any field, I don't care what it is, the rational numbers, Z mod 2, rational functions over a field of any variable, that field will have an algebraic closure. And what the algebraic closure is a field that contains it, such that every polynomial with coefficients in the base field has a root in the big one, right? And an algebraic closure is always as small as possible. And essentially what you do is you adjoin all roots of all possible polynomials. Now, it's trickier than that. There are some problems that you have to avoid, and there's a Zorn's lemma argument that you have to make, right? But so for example, if you look at the rational numbers, there is an algebraic closure that basically you would join all the roots of all possible polynomials as rational coefficients. But that field is countable. It's much smaller than complex numbers. Now, the complex numbers is algebraically closed. What that means is there's no algebraic extensions of it, right? Which means that every polynomial with complex coefficients factors into linears, right? But it's way overkill, right? You don't need things like E and pi to get the algebraic closure of Q. But that goes for any field, Z mod 2Z, right? There's an algebraic closure of that.
Like if you take the algebraic closure of a field, is that closure algebraically closed in general?
Yes. Yeah, that's it. Yeah, it is a closure operation. So when you take a field and you take its algebraic closure, that field is algebraically closed in the sense that, so what it means to be the algebraic closure is the field you started with, all its polynomials have roots here. Yay for that. But this also is true for this. This one is also algebraically closed, right? So if you have polynomials with roots from here, they're all algebraic.
So F is algebraic over K if the algebraic closure of K is all of F.
No, the algebraic, well, I don't want to answer that question because I gotta be careful not to mislead. If F is algebraic over K, then that's all there is to it. That just means every element in F is a root of some polynomial with coefficients in K, right? It does not mean that every possible polynomial with coefficients K has a root in F, right?
Oh, because there's.
So for
okay.
example, if you look at Q adjoined with I, right? So it's just sort of like the Gaussian rational number. So it's A plus BI where A and B are, that is algebraic over Q. But it's certainly not algebraically closed, right? Because that field doesn't contain a square root of 2, for example.
Okay. So also so R is transcendental over Q because you can find a root there's an element in quadrant, not a root. But then like, if you have like square root two, like Q adjoins square root two, is that algebraic over Q?
Yes,
Wait, okay,
and I actually. I'll prove that two ways. Uh. 3 ways. Stop before more ways come up. So. You know what the degree of this extension is? 2, that's right. Any finite extension is algebraic. The converse is not necessarily true. You can have infinite extensions. An infinite extension may or may not be algebraic, but this one for sure is algebraic. A typical element. Well, yeah, I'm gonna figure out this polynomial a couple of ways. I'm gonna do kind of a linear algebra, get on your bulldozer sort of way, and then I'll do one that sort of smacks of a little bit more sophistication. So let X right? So let X be that thing. This is a squared plus 2. Everybody cool with that? Now it's just a bunch of linear algebra to figure out how to make this work. The first thing is I want to get rid of this radical 2 crap, right? So notice if I multiply, this is going to be minus 2a squared minus 2ab radical 2, right? Anybody agree with that? And the reason I multiply this by minus 2a is I'm just trying to kill this thing that's got that radical 2 in it. That's my goal. So if I add up both sides of this equation, I get minus a squared plus 2b squared. Right? And here's my polynomial. So my X is a root of that quadratic polynomial. Everybody okay with that? So that shows that everything in Q radical 2 is algebraic because you give me this element here and that's how you form its polynomial. Multiply the a part by 2 and then take this norm thing, a squared minus 2b squared to get this. These are all rational coefficients. Everybody okay with that? Now, here's a way that's might perhaps a little bit more sophisticated. What's the irreducible polynomial of this? Well, I want a plus b radical 2 to be one root, right? What should the other root be? Well, from what I know in Galois theory, it should be the automorphic image of that one root, right? Because automorphisms of q radical 2 over q should take one root of an irreducible polynomial over rationals to another one, right? What automorphisms you can take a plus b radical 2. One place is to itself. Where's the other place you can take it?
A minus B radical.
That's right, to the conjugate. This is basically induced by taking radical two. Notice kind of the polynomial that makes this work is x squared minus two roots of that are plus two, or radical two and minus radical two. There should be two roots to this, one for each automorphic image in this particular case. And if you multiply this out, that's x squared. These cancel out here and I get minus two ax. And then I get the product of these, which is a squared minus two p squared. So I'll reproduce my polynomial. So long answer, yes, everything there is algebraic. Right.
So if there is like a bigger like, if there's a bigger polynomial that, a plus b squared square root two is a root of, you just take whatever the smallest degree of.
That's
Well,
right.
this is
So
a-
here's kind of an interesting thing here. So let me prove following. This can be kind of a fun thing to prove. Uh, Suppose alpha is algebraic over F. Show there exists a unique monic minimal polynomial. F of x and fx such that f of alpha is equal to 0. I think this kind of addresses the comment you have, as you said, well, what if there's a bigger polynomial? There is a smallest, and in fact, that small. Does anybody know what's the machine that's going to make this work? The fact that there actually is a minimal polynomial.
Yeah.
And you're on the right track. You need a little bit more though.
Yeah.
Yeah, that's right. So. Since alpha is algebraic, there exists g of x and f of x such that g of alpha is 0. And let me be really careful about this. I don't want to let g of x be the 0 polynomial because everything's a root of that. Right? So I know that there is some non-zero polynomial that annihilates alpha, right? So let's let I equal the set of h of x and f of x such that h of alpha is 0 alpha. Anybody got an idea for what kind of structure I has? That's not an ideal answer.
Oh,
Right.
Oh,
You're not used to that crap yet, seriously.
I was wondering, what is an ideal?
Oh, the I.
I thought it was for index. That's why I was like, post that, yeah.
In fact, not only is this an ideal, it's prime ideal, right? Which might be a little bit surprising. We'll prove that. Okay. Okay, so let's prove it's an ideal. Notice that it's not empty.
Well, you didn't need a prime ideal to show its principle, correct?
No. It's gonna be a principal ideal because you're living in a PID.
Yeah, exactly.
Right. I is not empty because, G of X is in I. And so, and actually, technically zero's in I as well, but I wanted to make sure that this is a non-zero ideal. So let, and I is not zero. So let's say H1 of X, H2 of X in I, and R of X in R, or I'm sorry, in FX. I'm gonna do my ideal criteria. Right? If you look at H1 of X plus R of X, H2 of X, evaluated at alpha. So it's an ideal, right? And in fact, it's a prime ideal. If, all right, G of X times H of X is in I. This implies G of alpha times H of alpha is equal to 0. Therefore, G of alpha is equal to 0, or H of alpha is equal to 0. So G of X is in I, or H of X. So I is prime. I didn't actually prove that, but it's worth noting. So it is generated Fx is a PID. I is generated by Fx. And here we can assume Fx is monic. Because if it's not, I'll just divide through by its leading coefficient, its highest degree coefficient, which of course is a unit in Fx. So I guess it's monic. So in particular, Sophia, I'll go further and say this one right here, since f of x is monic, this is unique, smallest with respect to degree polynomial, such that f of alpha is 0. Right, because the zero polynomial doesn't have a degree. So f of x is monic, so this is the unique smallest polynomial such that f of alpha is 0. And not only that, so if you find any other polynomial such that, say g of x, and you plug in alpha and you get 0, that means f of x must divide g of x. So it divides all the other ones with that property. Yes.
Why again do you get the monic thing?
Oh, because if it's not, right? So suppose your polynomial is, yeah, suppose it's something like 2x squared plus 1. That's not monic, just multiply by 1/2. Yeah.
Why do you? How do you know that it's of smallest degree there?
Because it has to divide every other polynomial that has that property.
Is f adjoint x also Euclidean?
It is.
Okay. That's where you get that, so you have your degree as your Euclidean.
Well, I mean, really, all we need at this point is the fact that it's PID, right? But yeah, I mean, the easiest way to prove that FX is PID is to show it's Euclidean, because it's actually easier to show. You know, it is kind of interesting because when you had 4120, how many of you had, so some of you had me, some of you had somebody else. How many of you saw that a Euclidean domain is a PID and a PID is a UFD, right? This is an old chestnut. Everybody does this in algebra, almost everybody, I guess. The proof that Euclidean implies PID is fairly straightforward. The connection there is very good if you can find the Euclidean function, which doesn't always exist. But the proof that Euclidean implies PID is not difficult. Do you remember the proof PID implies UFD?
There was choice.
That's right. No matter how you danced around that. So in a lot of algebra books, they'll do this business where they show that an ascending chain of principal ideals must stabilize at some point. There's different ways that I do it a different way. There are different ways that they do this kind of thing in books. Somewhere buried in there will be the axiom of choice, Zorn's lemma. In fact, it was funny because you were asking about those talks. I actually gave a talk in Austria about this kind of thing, an address on this. And one of the things I looked up for the talk, because I mean, I use this stuff, but I've never been as good with math history as I want to be, but I looked this up. There was a paper written in about, I think it was 76, by this mad logician, right? The person wasn't really an algebraist, but a foundations kind of person. So he wrote this paper, and I thought this was really funny. He proved in that paper that you cannot prove that a PID is a UFD without choice, right? You can't do it with the ZF axioms without choice. Can't be done, right? So you throw in choice to do that. And not only that, you can't even prove that a principal ideal domain has a maximal ideal without choice, which I thought, okay, so that makes me even more pro-choice. So.
Question just about like the definition of tensor product. Could you just re-explain? Because I'm just confused on,
You can see tensor products.
I'm assuming yes.
It wasn't for the last exam, so.
Yeah, it's nice. I'm just.
You could have just said that.
No.
Wait, what? Oh, so it's not on this exam?
Oh, I don't know. I'm not done with the exam yet.
He said he was looking at modules over PID and all, so.
Oh.
Thanks for giving.
Yeah. Thanks for that.
So they're gonna burn you and everything.
Yeah.
No, ask your question. So what's the question about tensor products?
I'm just like, so, like, by the definition of tensor products, like, A1 plus A2 comma B, that's related to A1 comma B, which is related to A2 comma B.
Well, so what you do is, let's see, I can do this. Are we already using the tensor notation? Or were you talking about when we were modding out? Are you talking about elements or are you talking about?
Yeah, the elements of, K,
Right.
yeah, K is generated by the elements. of-
Right, so F is free on A cross B, all this crap here, all that abstract nonsense
Which, what does that mean?
is subgroup generated by relations of the form. See if I can remember it right. It's generated by relation to the form A1 plus A2 comma B minus A1 comma B, A2 comma B. A comma B one plus B two equals, oops, minus A comma B one, A comma B two. And then R, well. Is this what you were talking about?
Mhm.
And you take the subgroup generated by all this. and you
Does
find out.
F being free on A cross B mean that like the basis of F is elements of A cross B?
That's right.
Okay.
You take every stinking element of A cross B and treat it as a separate basis element. That's what you do to make F.
All of A cross B? or
That's
it could
right.
be-
Every different AI cross BJ is a different basis element. It is a huge mess.
Okay, so it can't be less
But
than
then-
the number of elements.
Here you cut the grass, right? Because what you do is now you start imposing the relations that came from A and B in this right here. And so you have A1 plus A2 minus this. So this imposes new relations. This means that in the quotient, what you get is, well, first of all, the symbol A tensor B is shorthand for, because people didn't want to write that stupid coset all the time, right? This is just a shorthand notation for this. And these relations form so for example, it's A1 tensor B, it's A2 tensor B, and et cetera, right? And this last one is like RA tensor B is A tensor RB, and we can define this to be. So we have these relations here. So once you get back down to these symbols here, there are two things imposed. These relations are uniformly imposed, and you might have other relations that come back from, come back from the relations in A, in the sense that, so for example, here, back in F, you would treat A, when you build F, these are two different basis elements. They're totally independent, right? When you bring it back here and impose these relations, now, if what you do is you have A plus negative A, this will now drop out to zero, right? It was treated differently here, but when you impose these relations, it squeezes things in, and it imposes these relations right here, this one, and this one. And also you get back to relations that you had in A and B.
So negative A comma B, that's related to A comma negative B? Is that right?
Not here. Here, these are all different.
Mhm.
These are all different things in F. But when you impose these relations from K, when you mod out by that, that starts identifying some of this stuff.
Okay.
All right, that's what'll happen.
So if you're working over a, like, instead of multiplying by R in a ring, instead you have R in a field. Does that mean that RA tensor one over R times B? Is that equal to A tensor B?
So what's the question here?
So
So
like, imagine if your R is a unit,
uh,
essentially, so then RA tensor B over R is equal to A tensor B.
RA tensor B over R, yes. That's correct. If R is a unit, yeah.
If you have A1 comma B1. Oh wait. So A1 is related to B. And then if B equals B1, then does that mean A1 plus A2 comma B is related to A comma B1 plus B2?
I'm not sure. Let's write this down. So the question is,
If you have like A1 comma B. And then like A comma B1. Then does that mean that A1 comma B is related to A comma B1 plus B2? Since A comma B1 is related to A comma B1 plus B2? Wait,
well, so.
oh yeah, A equals A1.
Oh,
Yeah.
A equals A1. And what am I doing? Am I adding these?
You just, wait. Yes,
So this is really A1 tensor B plus A tensor B1. But now you're going to demand that these two are the same. So this is A tensor B plus A tensor B1. And yes, that would equal A tensor B plus B1. Is that what you were asking?
so for those, like the top two relations, would that make like the first four
Yeah, so
related to each other?
when you use these relations to generate K, what you're saying is in the quotient field, what's going to happen, or in the quotient field, I'm sorry, in the quotient module, you're going to have this happen. You're going to have A1 plus A2 comma B plus K. Well, so let me write this out specifically. A2B. This is in K. Right? And because that's one of the kind of, this is a family of relations we have. So that means that A1 plus A2 comma B is equal to plus K equals A1 comma B plus A2 comma B. Because this difference, this minus this blob here is in K, means that these two cosets are the same, right? And so writing this with our new notation, this is really A1 plus A2 tensor B. This is the coset A1 tensor B. And this is the coset A2 tensor B. So that relation here, when you're saying that these things are all in K, what you're saying is this always happens in the quotient, the tensor product, right? And same thing off the other side. This relation, or elements of this form are always in K. So you're saying when you go mod K, this coset is equal to this coset plus this coset, or the other tensor. Does that make sense?
Yes.
Yes.
So if you have, A direct sum B, then you have, the tuple, A comma B plus, negative A, comma negative B, right?
In the direct sum, yeah.
In the direct sum, that's zero.
Yes. Zero,
But if
zero.
you had this, the equivalent in the tensor product of A and B, you get 2 times the A tensor B.
Well, I mean, if you had, so you're asking what you'd have here, so if you had, yeah, I guess you probably would, because if you have. This is what you're talking about,
Yes.
right? Right, so you can bullet -1 across the tensor, and this is A tensor B plus A tensor B. I mean, assuming nothing stupid, like the ring doesn't have a 1, but I'll assume that. So this is 2 A tensor B.
Right. Which differs from like the direct product, where that would end up the zero.
Well, there's no, this tensor product emulates sort of multiplication, right? Because it comes off of those bilinear maps in a certain sense.
Well, we don't need to know this for these.
Well, look, don't go throwing Sophia under the bus, because when I looked under definitions and stuff, yeah, my exam's fluid until I'm done with it, so.
For a finite extension, or for a extension field that's of finite the degree is, yeah, finite.
Yep.
Does that mean, that doesn't mean though, that both of them are finite? Like both the fields are finite?
Oh, no,
Okay.
almost never, yeah.
Okay. But being finitely generated, like if F is. So an infinite field can be finitely generated though?
Over something, right? So just take Q itself. That's the smallest infinite field I can think of. Usually when you talk about a field being finitely generated, you're talking about it being finitely generated over another field. Now, there's no field for Q to go under. So as a ring, it's not really finitely generated, is it? Because you have to invert infinitely many primes, right? So as a ring, the field Q, well, so the ring Z is certainly finitely generated because all you have to do is take its one and it generates the whole thing, right? But now to get to Q, you have to get to Q as a ring, because there aren't any fields yet, you're still down in domain land, and Q is the smallest field. If you only sort of add on finitely many things over Z to generate it, then there exists some prime that is bigger than all those things you adjoined. If you adjoin n things to Z, there's some prime that's bigger than all that. And there's no way that you're going to generate, so you could stick on fractions here. So let me be more precise in what I'm saying. So suppose you take Z, we're trying to build a cube. And you see A1 over B1, A2 over B2, AN over BN. And I will assume, just for ease, the GCD AI BI is equal to 1. So my fractions are all reduced. Right? Can this be Q? And the answer is no. Q is still too big for that. Because, and I'll prove it, let P be the largest prime. Such that P divides some AI over BI. Now let Q be the prime larger. Let me say strictly. But now that I think about it, I think I probably want to go by induction, right? All right, so I'll keep with this notation. So we go by induction on N. To show the A1 over B1 up to AN over BN is strictly contained in Q. So you can never do this with finite many fractions. If N equals 1, we claim, I claim. There exists a largest prime. P such that, there exists X in Z A1 over B1 of form N over P. So as there's a largest prime you can find in the denominator. Notice that maybe this prime appears to a certain power. I could just multiply it down until I get a single P in the denominator. All right. Prove let Q bigger than largest prime dividing B1. Suppose N over Q, where Q does not divide N, is N Z A1 over B1. This implies N over Q equals M0 plus M1 A1 over B1 plus MK A1 over B1 K. Right? Now multiply through all these denominators, multiply this by B1 to the K, Q. And over here, I'll get N times B1 to the K is equal to M0 B1 to the K Q plus M1 A1 B1 to the K minus 1 Q plus MK A1K Q. Notice that Q divides this side of the equation. So Q divides N times B1 to the K. And that's a contradiction because we assume that Q doesn't divide N, fraction was reduced, and we know that Q doesn't divide B1. And now, you just go by induction, assume it's true, and then add one more thing, and the proof is essentially the same. So Q as a ring is not finitely generated. It's just, I mean, yeah, there's no field to generate it over. Q adjoined with I is finitely generated over Q, right? And so you're allowing yourself to use elements of Q to do it. Yes.
In general, your Galois group is gonna be SN, where N is in natural.
So we're going to get to that when we talk about Galois groups. So if you take, well, the polynomial needs to be separable, but if we think about characteristic 2, then, or I'm sorry, characteristic 0, we're good to go. Suppose you have an irreducible polynomial of degree n. So this is kind of another spoiler looking ahead. If you have an irreducible polynomial, say over Q of degree n, then if you take all the roots of that polynomial and you dump them into Q, you will get a Galois extension, right? And the Galois group will be a subgroup of Sn. And in fact, it'll be a transitive subgroup. Anybody remember what transitive means? Transitive subgroup of Sn. It means if you take any two elements in, so Sn is acting on the letters 1, 2, 3 up to N, right? Take any two I and J, there's something in that subgroup that swaps I and J. or I shouldn't say swaps, that's bad. Given any I and J, there's something in that group that takes I to J, right? So, for example,
It's a subgroup generated by like the two, like this transpositions.
let me give you an important example. This is let's look actually in S4. In S4, well, we'll see. Let me remind us here. Let's say H and SN is transitive. If given one I, J, well. Any two I and J between one and N, there exists sigma and H with sigma I equals J. That's what it means to be trained. Now, let me give you an example. Of course, let me point out that, as it turns out, SN is always transitive, right? Because I'll tell you what takes I to J, permutation IJ, right? And even though it may not seem like it, AN is always transitive as well. As long as N is at least 3, right? Because you have 3 cycles. So if you want I going to J, just do IJ and put in K. And if you've got at least 3 things in there, you've got enough to go, right? So these are transitive. Let me give you a good example. And this is another kind of interesting thing about groups. There is a subgroup of S4. I agree with that. It's pretty obviously a subgroup, isn't it? Because 1, 2 times 3, 4 is 1, 2, 3, 4. This is a billion. It's actually isomorphic to Z2, Z2. It is not transitive, right? Because there's no way to take 1 to 3, for example. Not transitive. I agree with them. And this is isomorphic to Z2, Z2. And there are other copies of this, right? I could have played other names with this. E 1, 3, 2, 4, 1, 3, 2, 4. This is also isomorphic to Z2, Z2, but it's not transitive. But there is a subgroup of S4 isomorphic to Z2, Z2 that is transitive. Anybody know what it is? What's that? No, that's not isomorphic to Z2, Z2. There's a subgroup with 4 elements that's transitive. I think this is a weird example. It's not really clear that this actually is a subgroup, is it? Right? But notice if you multiply these 2 elements, 1 goes to 3 to 4, 4 goes to 2 to 1. 2 goes to 4 to 3, and 3 goes to 1 to 2. So the product of these two is this. This is totally weird, isn't it? But this is transitive because given any 1, 2, 3, 4, just pick any two of them. This takes 1 to 2, this takes 1 to 3, this takes 1 to 4, and just go through them all. This takes care of you. So that's really weird. S4 has a bunch of subgroups of order 4 that are isomorphic, but that's the only one that's transitive, right? So here's what we're going to talk about. Okay, the camera's not looking. How many of y'all know the quadratic formula? Oh, yes. Lots of nods out there. Right. Here's one of the reasons it's kind of easy, right? If this is polynomial, it's got, if this polynomial is irreducible over field, it's got 2 roots, right? Well, let's say characteristic 0, just to make my life easier when I'm talking about this. The Galois group, if I take all the roots of this, and there'll be 2 of them, and dump them into the rationals, the Galois group will be a transitive subgroup of Z2, or I'm sorry, S2. And S2 is isomorphic. There's only one transitive subgroup of S2. It's Z2. That's it. And that's why quadratics are so easy in a certain sense. There's only the identity of one non-trivial automorphism. What about this? What if this is irreducible? Transitive subgroup. S3. I know what the transitive subgroups are. This time there have to be 2 of them at least. S3 and A3. The cubic is more complex to solve because we saw an example with the Galois group S3. Namely, it was x cubed minus 2. Remember that first example we did with the Galois theory? We had the Galois group was S3, wasn't it? It's harder to find these. You can actually find cubics with a cyclic order 3 Galois group, but you got to hunt those down. Those are, if you pick one at random, it's going to be this, right? An irreducible cubic. You've probably seen the cubic formula at some point, right? Maybe you didn't memorize it or anything, but how many of you have seen it at some point, right? How many of you seen the quartic formula? Yeah.
Bert showed it.
Oh crap, yeah, you did.
He flashed it on the screen at a font too small.
It
to
was
see.
a jump scare.
Oh, yeah, he did it. Yeah, it is a jump scare. I used to actually do that in Cal 1 because this would be my, well, it was my justification for doing, what's that?
Like grouping.
No, implicit differentiation.
Oh,
Because if you take something like this, suppose I want to know what this looks like. This is some curve you might encounter in calculus. You can actually use the quartic formula to find this. But there's multiple roots. Which one do you pick with a radical? I used to seriously, it was like, it scrolled over like 2 pages. What the thing is, it's like, okay, who wants to take a derivative of this, right? Because it's full of square roots, quartic, cube roots, and fourth roots of, x and so forth. Or do you want to just do implicit differentiation? It's much easier, right? So, do you know how many transitive subgroups there are of S4? There's 5 of them. There's always these. There is the dihedral group on the square and the cyclic group of order 4. Any cyclic group has to be transit. If you're an SN, the cyclic group of order N, the N cycle has to be transitive because you've got any I and J appears in that cycle. And even though it might not take I directly to J, if you take a big enough power, it'll jump to J, right? So anytime you have an N cycle in Sn, then it's gotta be a transitive group. And you have this one, which is not all of them, just this one right here is transitive. These other ones they're dead ends. These groups are all solvable. That's why Burke could flash his formula for the quartic, right? S5. Anybody, I guess how many subgroups there are here? No, there's 5. Anything that contains a 5 cycle mark. So we've got dihedral on the pentagon, we've got cyclic 4 or 5, and there's a weird one. F20. This is a Frobenius group of order 20. It's generated by a particular 5 cycle and a 4 cycle. We'll talk about that later. That one shows up if you take like, do you remember when we talked about the 5th root of 2 and I said, oh, look at these 4th roots of unity? That'll show up there because we had an extension of degree 5, an extension of degree 4. When you get all the roots, I'm gonna have this one show up. If your Galois group for the polynomial, these 3, you can solve it in terms of radicals. You can find a formula for it and solve it in terms of radicals. These 2, you're out of luck because they're not solvable. So they have solutions, but you can't write them in terms of square roots, sums, products, things like this. For S6, that's where I quit because if I remember right, there are 16 subgroups, transitive subgroups of S6 that are transitive. And so we're going to quit there. And as you might guess, as it gets up, I think when you get to S7, there's only 7 again, but with 8, it's out of control, 15, something like this. So, yes.
You said the C4 and C5 were the cyclic subgroups?
Yes, this is cyclic of order 5. The one in, well, actually, and there's a bunch of them, and they're all transitive, but they're generated by any 5 cycle. That little subgroup is generated by 5 cycle.
Is there a reason why, like, the pattern of number of the subgroups is so weird? Like, you go from 1 to 2 to 5, 5 to 16, and 7.
I don't know. That's question 1 when I get to the pearly gates or wherever I end up. But yeah, so I'll give you another one. So here, okay, so we used to play this little numbers game at lunch sometimes when I was in Fargo. So I want to give you a function on the integers and see if you can guess what it is.
Yeah, after 7, it goes to 50.
Okay. So I want you to guess the function in f of n. F of 1 is 1. Any guesses? No. Can you guess what the function is?
Oh. 1.
Okay, that's a great guess. Doesn't work. F of 2 is 1. Oh, your conjecture still works, but I assure you it's not true. F of 3.
Okay.
F of 4 is 2. F of 5 is 1. F of 6 is 2. F of 7 is 1. Yes.
How many like distinct factors it has in the integers?
No, but.
Not distinct.
No, good. F of 8 is 5. You guys got to guess this before I'm not able to produce this. F of 9 is 2.
How many ways to write it, decompose it, like.
F of 10 is 2. F of 11 is 1. F of 12 is 5. F of 13 is 1. Any conjectures on, let's take this. Any conjectures on what happens on all the primes?
One.
Okay, right. So that's something. So we'll get this. So it turns out that F of P is 1 for all P prime.
Square, prime squared, like p to the n has n. Or, no, I take that back, but, p squared has 2.
Okay. This is also true. I'll give you credit for that. F of 14 is 2. 15 is 1. 16 is, now I'm getting a little shaky. I think this is 14. But I won't venture a guess. 17, 1. 18, it might be 3, maybe. Actually, so I'm starting to fade on whether I'm getting numbers right. Anybody want to guess? I'll give you a hint, it has something to do with groups.
Groups.
It's the number of isomorphism types of groups for every possible n, right? There's one group of order 1, one of order any prime, f of p squared is 2, f of p cubed is going to be 5, I think, in general, et cetera, et cetera. So, to your comment earlier, here is an unknown question. Is this function onto? That is not known. So, for example, 7, can I find some number out there where there's exactly 7 isomorphism types of a group of that order? Okay, it's my understanding it's an open problem. And I learned about this from one of my favorite professors when I was a grad student. And given this kind of problem, I'm pretty sure it's probably not solved. So.
Is it also an open question of why there are those numbers for groups of those?
Oh, yeah. I mean, it's, these groups, doing these kind of finite group stuff it's hard work because it requires a lot of kind of very careful and clever counting kind of arguments, right? And I'm sure that you can look around in the literature. Like, I'll give you another one. Like, I mean, how many rings of order 4 how many rings are there? That gets a little dicey. I think there's, I can't remember, I don't even remember what the number is. It's something like 7 or 11, and it depends on whether you're allowing an identity or not, right? And it depends on whether you allow commutativity or not. And I think that, for example, for certain types, maybe rings of order P, this is probably known. Rings of order P cubed, maybe P squared, maybe P squared Q, things like this, it's known. But these problems that you can basically explain to somebody, almost day one after they've learned what a group is, can be very difficult. Yes.
Are you always gonna have an abelian subgroup of your Galois group?
Well, you've always got the identity.
Well, a non-trivial.
Oh, well, of course, any group, any non-identity group has to have a non-trivial abelian subgroup. Because if it's abelian and it's not the identity, this is certainly true. And if it's not abelian, take any element in there that's not the identity and look at the cyclic subgroup that it generates.
So C5 there is abelian.
Yes, that is correct. Oh, so maybe this is kind of to your question here. So one transitive subgroup of SN always. So I'll give you some stuff based on this. Here's what you're always going to find. SN, transitive subgroup. AN, transitive subgroup. cyclic of order n, transitive subgroup, dihedral, anything that contains an n cycle, right? So if it contains an n cycle, it has to be a transitive subgroup.
Is A3 isomorphic to C3?
Mhm.
Okay. And Z2 is isomorphic to S2
Mhm.
and C7.
Right. Right, those cases are a little bit kind of degenerate.
Law of small numbers.
Yeah. Yes.
This is totally different. Can you just, what is L double prime and like L triple prime define?
Oh, it's just, you just keep doing the primes to it, right?
Would it be like
So,
sigma of ES?
so L is some intermediate field, right? So you've got some, let's see. You've got some L sitting here between K and F. Whoops, I forgot to put the L there.
It's again.
Yeah. And G equals the Galois group, F over K. So you start with L, it's a field. Then you go to L prime, and this is a group. And this is just all the crap in G, such that sigma L is equal to L for all L and L. So this is just all the elements, all the automorphisms that fix everything in L. Now then you go back to field in L double prime. Well, this is L double prime is the set of, let's say, V and F. So it's everything in the field such that sigma V is equal to V for all V, sigma in L prime.
That's the field.
Right. So L prime is everything that fixes everything in L. Right? And then L double prime is everything in F that's fixed by everything that fixes L, right? So in particular, this contains L, maybe equal, but it contains L. Right? We like it and we say it's closed if we get equality here. But by the time you hit the next step, and we prove this in class, this one is an equality. So any prime is equal, if it's already primed, when you double prime it again, you get back to where you started. So that is, a prime is equal to its triple prime, right? So
L double prime is everything in F that is fixed by L? No.
Right.
that is fixed. Okay, this is a mouthful. It's everything, L double prime is everything in F that is fixed by everything that fixes L. Right? So everything that fixes L, but it might fix a little bit more. And that's what L double prime is, right? It's all of the stuff in L, and then maybe you get some bonus things that are fixed, right? And you might worry that this keeps growing, but this is the interesting part, is the weeds stop growing by the time you get here, right?
Okay, so you can't go like more because you're just restarting.
Yeah, so that's right. So once you hit L triple prime, you're back to L prime. So then it goes back and forth between L prime and L double.
And since F contains K,
Mhm.
you can just do that. You can do F contains K, so then K prime contains L prime contains F prime. You switch that.
Yeah, so right. So F contains L, so the primes are reversed,
Okay.
right? That's right. Oh. and they reverse in both directions.
And then this is the last question I have, but this is before projective and injective modules. I have a note in my notes that says any ring with identity is free with basis 1, like free with the basis R. For
Yeah,
the identity in the ring.
right.
What is that? Cause then.
That
what if-
means that any ring has an R module over itself.
Oh,
It's free
okay.
with basis 1. Yeah.
Oh, okay. And that just means like you can multiply any element in R by 1 and then generate. Okay.
That's exactly right. Did anybody talk to the other three in here? I hope I didn't scare them off like they thought for sure I wasn't gonna show up.
Bryce said he'd text me if he had any questions, but, I asked him if he did.
Adam said he wasn't planning on showing it.
What's that?
Adam said he wasn't planning on showing it.
Okay. All right.
That's the dice version.
He was. So close.
Just,
Oh.
I was funny, and I was like, I don't know.
Well, anything else?
I'd like to just check if the way that I proved three on the practice exam was right.
Okay, what?
It was the whole, if F is a finite extension of K, then F is algebraic, okay.
Oh, right. So what did you do?
The doing the set that was linearly independent, and then you add another element and it becomes dependent.
Right, right. So you have that, what was it? F is finite over K, right? So this is where we're going, let. Let U be in F. Actually, anything that you want in F. And what I want to do is show that U is algebraic. So the set. 1 U squared UN minus 1 UN must be linearly dependent. Because the size of the set exceeds the dimension of the vector space, right? So there's no choice for this to be linearly dependent. So there exists A0, A1, AN minus 1, AN, not all 0, such that A0 plus A1U plus A2U squared plus AN minus 1 UN minus 1 plus AN UN is equal to 0. Agreed? And since these are not all 0, then that means that U is the root of a polynomial. Just replace U with the X in this polynomial's root of. So you've shown that every U is algebraic. Does that make sense? Did you do it right?
So what is true? But we could also
do
like
this
to
whole
see
exam.
4 for the exam as well.
Let F be a field alpha non-zero containing. Show that alpha is algebraic if and only if 1 over alpha is in alpha. Okay, so. Yeah, this is actually kind of, there's a slick way that you can do this by quoting some theorems or whatnot. But I think I'll probably just, I'm gonna get my hands dirty here. F be a field, alpha a non-zero element. Show alpha is algebraic over F. If and only if one over alpha is in F joined with alpha. Right? So alpha is algebraic. Then A0 plus A1 alpha plus A2 alpha squared plus AN alpha N is equal to 0. I'll assume that this is the minimal polynomial. That is, I'm going to assume that AN is not 0 because otherwise I wouldn't have written it. And notice that if A0 is 0, that means that I can pull a factor of X out of the polynomial and have a small. Everybody okay with that? And I'm going to use both of those in a minute. This means that minus A0 is equal to alpha times A1 plus A2 alpha plus AN alpha to the N minus 1. Agree? So 1 is equal to alpha minus A1 over A0 minus A2 over A0 alpha minus AN over A0 alpha N minus 1. Agreed? And this is 1 over alpha. Because it's the multiplicative inverse of alpha. Okay, so far. On the other hand, suppose 1 over alpha is in F adjoined with alpha. So there exists A0, A1 up to AN in F with 1 over alpha equal A0 plus A1 alpha plus A2 alpha squared AN. Right? So 1 is equal to A0 alpha plus A1 alpha squared plus AN alpha N plus 1. And now we see that alpha is algebraic, right? Just bring that 1 over. That makes sense. What else we got?
He might be good.
How does that show that alpha is algebraic again? Like if it's not 0?
Because alpha,
Oh, because I guess we're.
let's see.
Oh, alpha over 1 equals 0. Oh.
Yeah, just.
There. So read it back. Nobody don't want to do it. So
And then that shows that 1 over alpha's in F.
oh, yeah,
because-
yeah, yeah. You're right to
One-
tell me about that for sure, because what this means is notice that this thing is in, by definition, this is in F alpha, right? Because each AI over A zero is an element of F. And it's a linear combination of those things over powers of alpha, so that's in F alpha. So one over alpha is, I should have made a deal out of that.
So is one over alpha, it's one over alpha because it's equal to one, like alpha times.
That's right, because when you multiply by alpha, you get one, so it's no choice, because the multiplicative inverse of an element, if it exists in a domain or in a field, is unique.
Okay, so would the multiplicative inverse always just be one over alpha? Is that?
That's one way to think about it, yeah.
Okay.
So easy. Yeah, and I know for a fact it was not gonna be